Okay. So I actually will like to start, right? So I would like to welcome all of you who are joining us through the Zoom as well as the YouTube platform for this edition of the NSF Wednesday Colloquium. So one of the things that I would like to mention that this series has sort of attracted top scientists from India and abroad who are working in various areas of physics, chemistry, and biology. And today is no different. We have Professor G. Aravind from the Indian Institute of Technology, Madras, joining us actually physically for this colloquium. We are actually lucky that travel is kind of easier now post third round of COVID. And I'd like to also sort of mention that it would be this particular talk is, of course, being live on Zoom, but it's also being put on YouTube channel. So any of the material that you find you would like to sort of go back, you can always go back to the TIFR Platinum Jubilees YouTube channel, and you can look back at the talk again. Revisit the talk again. So without further ado, I would request my colleague, Professor Vaibhav Prabhudesai, to actually introduce the speaker, because the speaker himself is one of our own, one of our PhD students who's coming back and giving this colloquium. So
yeah, thanks, Jyotishman. Yeah, so it gives me great pleasure to introduce my friend, Professor G. Aravind from IIT Madras. Aravind did his PhD from TIFR in 2007 in photo detachment and dissociation of negative ions. And then he did his postdoc from Aarhus University on ion traps and looking at the submicrosecond photo dissociation lifetime studies. And then in University of Basel, where he participated in developing a state-of-art 22-pole trap for ion trap. And then subsequently in 2010, he joined IIT Madras. And after that, he is there. Aravind has won, he was a recipient of Geeta Udgaonkar Best Thesis Award in Physics in 2007. And also INSA Young Scientist in 2012. His research interests are probing the structures and dynamics of molecules in interstellar medium, relevant to interstellar medium. And he does that using photoelectron spectroscopy, dissociative photoionization, and ion traps in the laboratories. And today he's going to talk about an unusual ionization mechanism that they have discovered in unbound molecules in their laboratory. So, Aravind, thank you.
Thank you. Thank you very much, Vaibhav, for a nice introduction. And I would like to thank the organizing committee for giving me this opportunity here to talk about our recent work on ionization mechanism. So I come from IIT Madras. It's a huge, I don't know how many of you have visited it. It's a huge campus. It's a huge very huge green campus, very huge for TIFR dimensions. So it's a very huge green campus, and we have a lot of black bug in the campus, many of them, and we also have deer in the campus, and also despite not being through JEE, we also have them here. So that guy attends classes. Sometimes he does. Yeah. So today, before we talk about this unusual ionization in unborn molecules, we will discuss in some detail about a specific ionization mechanism that operates in bound systems. Before we and then we talk about whether it can be operative in unborn molecules as well. So, if you consider ionization, the most of the reactions that happen in our environment the starting point is creating an ion, and then you have the reactions then proceeding, for example, ion molecule reactions, etc. The idea is to understand this ionization mechanism. So there are several kinds of ionization mechanism, and depending on the environment where it happens, the different mechanism dominate over the other. So if you consider a molecule, when a molecule absorbs a photon of appropriate energy, it can be ionized, becoming a positive ion and detaching an electron. If the photon energy is exactly equal to the ionization potential, then you form the negative positive ion with a electron at rest. If the photon energy is above the ionization potential, then you can get a non-zero kinetic energy electron. But this single photon ionization is typically not that easy in most of the labs, because the ionization potential is of most of the molecules are above 8 eV. So you may need VUV lasers to do this single photon absorption. But if you don't have such laser, if you have, say, for example, a YAG laser of 4.6 eV energy per photon, you don't have to worry. You just have to focus these lasers so that you achieve very high intensity. Because at very high intensity, an atom could absorb more than one photon at a time and get ionized. So this is what we call as multiphoton ionization. And this happens typically at very high intensities. There is one important thing that we need to remember, that in such cases, if you consider the rate of the yield for the positive ions, it is proportional to the nth power of the laser intensity, where n is the order of the process. If it is a two-photon process, then the rate is proportional to laser intensity squared. So if you take the ln of this and plot it, you get a straight line whose slope will give you the order of the process. This is something that I would request you to just remember, those who are not in this field. Now, let us consider some very interesting situation where just inertial ionization of atoms. I can classify the electrons as core electrons, which are more tightly bound, and valence electrons, which are higher in energy. Now, if this atom absorbs, say, an X-ray photon, I could eject an electron from the core electron, creating a hole, okay, or a vacancy. This hole is unstable. It will soon decay, in the sense that an electron from the valence level would drop down to the vacancy. Now, when an electron from a higher energy level drops down to a lower energy level, there is a difference. This difference in energy should be emitted. That is the energy, excess energy in the system. In some cases, this excess energy would be sufficient to eject an electron from the outer shell. This is what we call as OJ electron, OJ process. There are many friends here who worked with it in DNAP. And yeah, so what we did was we had a photon which created a hole, inner hole, which which decayed, and then which means that the hole from an electron from the higher level dropped in, and the excess energy is taking out an OJ electron. Okay. Now, this OJ decay is a very fast process, but it does not always occur whenever you have an inertial ionization. Okay. Let us consider a very interesting situation here. You have a neon atom, and the first ionization potential, what I mean is the energy that you need to remove a 2s electron from neon atom, it is around 48 eV. And the same for removing the 2p electron is about 21.8 eV. Now, if I shine a photon of appropriate energy and create a 2s hole, you see that this 2s hole is energetically above the 2p hole state. So it has to decay down to the 2p hole state, which means that essentially that you have 2s above 2p by 26.84 eV, which means that an electron from the 2p level will drop down to this hole. Okay, 2s hole decays to a 2p hole. Now, we have now created a neon cation. There is an excess energy now of 26.84 eV in the system, but unfortunately, this energy is not sufficient to remove another electron from the 2p level from the neon cation. Okay, so what happens is this is insufficient, and hence the doubly ionized state of the neon atom is energetically forbidden.
Yeah, sorry, this is very maybe. No question is to be question.
Like, so the scenario that you are showing that in the EV that 48 EV for the 2s and then 22 or whatever for 2p.
Yeah.
So this scenario, I mean, for any atom, I can think of that the higher, I mean, the 2p thing. So, or is it only like some neon is typical of this kind of atom where this situation is there, or it is true for all atom? I mean,
The outer shell, what is true for all atoms is so is higher level than 2s.
right. So
Energies could vary depending on the atom, of course.
right. But this scenario, so I was thinking whether there is something specific for neon you are looking at.
Actually, this, the energy concept that I mentioned, it doesn't occur for every inertial. It depends also on set. If you have very high Z system, it doesn't happen. Usually, ready to decay happens. Okay, so there is this in this case of neon atom. Okay, the energetically it is not also possible to create OJ process. Now,
how much is the binding energy for nickel neon 2p?
Yeah.
It is ionized.
I'm going to do that.
Yeah, that was my question also.
That's the second one.
Yeah.
That's the second one.
Right.
Okay, it's there right away here. It's 61 EV. Okay, but yeah, I'm just coming to that. Now you have a doubly ionized neon cation. Now this is energetically forbidden. So what happens? This excess energy cannot knock out another electron from 2p. So it has to be emitted as a photon. And this lifetime for this is about 0.2 nanoseconds. Now, why was this insufficient to remove an electron from the 2p level? The amount of energy that I need to remove for a 2p electron is 21.8 eV for a neon atom. But now when I want to remove the electron, another electron from the 2p level from a neon cation, it is energetically expensive because it's more tightly bound now. It's a cation now. In other words, there is a very strong repulsion between the two holes which are residing in the same atom. So it's a higher level, energetically higher level state. It is expensive to achieve it. So now, what happens is, which means that the bottleneck is essentially having two holes in the same site. We learned that from this. So let us try something different. Very interesting, fascinating situation of another monomer. So we have a dimer situation now, neon dimer. Now in this case, again, there is not much difference between the ionization potential for 2s and 2p electron from a single site. And the double ionization potential, which are the potentials to remove 2 electrons from neon, is also not differing much. However, the double ionization potential, when you have electrons removed from 2 electrons removed, one from each site, is drastically reduced. It goes to 45 eV, which means an initial 2s hole in site number 1 that you create by photon could decay down to 45 because it is energetically above this 45 two site double ionization level. Therefore, what happens is an electron from the neighbor gets kicked out. So this is called essentially this happens because I have a Coulomb electron correlation between these two systems, and excitation in an excited atom relaxes and the excess energy ionizes its neighbor. Okay, this is very important process because you don't find atoms or molecules which are isolated in system. You always in nature find most of the time it is in an environment. So this is an efficient decay process. Why? Because radiative decays are in nanoseconds, and the decay time for this is in femtoseconds, 60 femtoseconds. Yeah.
Can I ask?
Yeah. Yes, sir.
Okay, wait. I'll just give that.
Sorry. No, this neon ions that you are talking about.
Yeah.
So they are, of course, stable ions and they are independent. They are not hybridized, isn't it? Or you are talking about they are hybridized?
They are
These two neon dimers means that you are they are electronically they are.
Yeah, they are van der Waals clusters.
Huh?
They are van der Waals cluster.
I see. So why I'm saying, because normally neons are pretty stable. I mean, they're
So it's van der Waals cluster, weakly bond. It's about 2 milli-electron volt is the bond energy at the equilibrium distance.
Okay, so the question was that, I mean, normally, if of course one atom is in excited state.
Yeah.
Okay, so you are basically thinking the whole object is excited. It's a quantum mechanical process, and then the electron can come out from any of the atom. That you are trying to say?
No, not really, not that way. The excitation in one system, okay, when it de-excites, there is an electron correlation between these two because they are close by.
That's the point I'm asking. How much they are coupled to each other? Otherwise, you see that if one is, I mean, you have one transition from 2p to 2s.
Correct.
So the energy is stored there. So it's in an excited state.
Exactly.
So how much it can influence the neighboring neon? So that's the thing which is.
It can influence because there's a dipole interaction between the two systems. Okay, and what you need is an overlap of the outgoing electron with the wave functions or the two valence, the final host that you create. Okay, it turns out that if you calculate this. The thermal golden rule, the leading term of that, it turns out that it is very efficient process for exchanging energy from one excited system to the other.
Okay, I mean, I understand. I was thinking that you need to have a strong coupling. Otherwise, what happens is that I can think of like it emits a.
There is also another problem having a space.
In turn excites the other one. Yeah. So, but if it is a non-radiative, then you need to have strong coupling. So that was the thing which
I actually had a similar question in terms of the these are atoms, right? There is a process that is equivalent in molecules where electrons are not ejected, but excitations can be shared. And that's called singlet fission. It's like multi-exciton generation process where you have similar like OJ kind of a interaction. That means you have the excitation and then a non-radiative depopulation of that excitation to a lower energy triplets to create two triplets from a single photon. My question to you is, what kind of coupling is necessary for this particular process to happen? You say it's a van der Waals complex or binding, but is there a specific nature of the correlation, the electron correlation that you are talking about, or is that distance dependent?
It is distance dependent. Actually, it is distance dependent indeed, and the ICD rates go high when intermolecular distances are coming small.
And that can be controlled?
Yeah, when you make the system, it depends on the type of. If you take a neon system, dimer, it has its own equilibrium intermolecular distance. So there is not much of a control in that sense.
Okay. So to check that systematically, you have to construct synthetic.
Yes, exactly.
Okay.
Exactly.
Talking about the single molecule. Dimer. Okay.
It's 2 milli-electron volt that is internuclear for the equilibrium distance.
How many vibrational states are there?
It's a in the dimer. 2 milli-electron volt.
No, but
I don't think anything would be there. It's just vibrational levels are few, at least a few milli-electron volts, right? 50 milli-electron volts.
That depends on the
It's very shallow.
But that
separation of the interaction.
Since this is a dimer, the equilibrium distance will be far larger than the normal molecules, right?
It is. Yeah, it is actually 3 point.
That well is not too shallow. It's too shallow to have
multiple. You cannot have levels, vibration levels in that. Yeah.
Yeah, but
the distance is
one vibration level.
Yeah.
Okay. Okay. No, I was asking this because of this same question that if you could populate different vibration levels, then you have a control on the distance between the two classical pictures.
Correct.
Yeah, but
here it is.
Experiment goes on, but that's beyond this.
Yeah. Yeah, I understand. But
this is probably a very naive question. So, what is the difference between what you were saying here and you have one bound transition, then photon goes and
no, there is no bound transition. Yeah, okay, that's correct.
And then the photon goes and then photon energy.
There's an energy transfer that is through virtual photon that we see that, and the energy gets transferred from the de-excited system to the neighbor, an ionized system.
The time scale also will.
The time scale is also different, of course.
For what?
So he's asking, what is the difference between this ejection
Which the second one?
What you are describing.
Yeah.
Vis-a-vis, one bound transition happens, photon comes out, and ionization is the next step.
The second one is ultra fast because it is in. Oh God. Yeah, the second one is ultra fast because it is involving electron correlation. It is in femtoseconds time scale. And the OJ, the internal bound ones will be not that fast.
Okay, and one more question. I see that you have used the local basis of the neon atom to define the orbitals, right? Now, is that a good approximation in this case that you define everything one side, two side based on the local side description of actually removing electron from a real 2p, or is it there is some interaction between the two 2p's to create a molecular orbital?
I'm not sure about this way the double ionizations are calculated.
Okay.
So, but what happens is that essentially the energy, if you the energy of the two when the two holes are separated over a distance, it just comes down.
Sure. Thanks.
Yeah. So now what happens is, I think I went very far. Yeah, sorry. So what you have is finally you create two neon cations and they explode. So this is fly away. So this is what we call as interatomic Columbic decay, and it is for the neon case as per calculation it is 60 femtosecond, which is 1,000 times faster than the radiative decay, which we just saw 0.2 nanoseconds. If you have it, if you have the radiative decay in a monomer. So wherever ICD is there possible, it dominates over the radiative decay. I'm going to do that. Yes. So it was first predicted. Yeah.
It's not possible to have double ionized dimer.
That's what we have, right?
No, dimer.
That's what doubly ionized dimer. Dimer, both the units are ionized, singly ionized. That's what I said. You're right. That's what I said. We will also have that variety coming up. Yeah. So now it was first theoretically predicted by Professor Sederbaum in HF molecular dimer, but I'm not sure whether this is experimentally verified in this dimer. This is a hydrogen bonded cluster, where again you see a 2s hole in the case of a monomer is energetically below the double ionization potential, whereas in the dimer case, the lowest double ionization potential is below the 2s hole. So the 2s hole can decay, same process can happen. So this is a non-local electronic decay mechanism. And what we described here is actually direct ICT, where you have a hole in one of the system decays and the energy is shared to the next adjacent neighbor, and the electron from the next level goes up. So you have a 2p hole. This is direct ICT. There is another process that is possible, wherein you have, what is this? Yeah. So the another thing that is possible is that you can have the initial hole that created could be filled by an electron from the neighbor. Okay, and then an electron from this acceptor can fly off. The initial and final states between these two are same, essentially. But we call this as exchange ICT because the electron is actually donated from the neighbor. And when we compare these two, exchange ICT is rather very weak for some reason. Okay. Now let us consider a very interesting situation of neon argon system dimer. I again create an initial hole in the neon, and I see that single hole neon with argon is energetically above neon with double hole in argon. Okay. What does it mean? So this state can decay to this state, which means that finally I will end up having no holes, a neutral neon and two holes in this. How can it happen? I have to just exchange an electron. There is an electron transfer mediated decay here. An electron gets transferred from argon to the 2s hole, and the excess energy kicks off an electron from argon. But this is also a possible energetically.
that you are creating this 2s.
Yeah.
Is it that you are using some resonant energy or something?
Yeah,
How do you
not resonant, it's a resonant, right? Because you are coupling to the continuum. You just need, when you have a photon of energy such that it can ionize a 2s
Well,
level,
it can also ionize the.
it can also.
Yeah, but so how do you know that this process is the one which?
Yeah,
is
we can
happening?
do that. I'll just tell you that, because
Okay.
even if I'm going to do that when I talk about experimental verification of neon diamonds, I'm going to talk.
Okay.
You will have that signal as well. You will when you are able to ionize 2s, you will also have a 2p ionization. Yeah.
I would expect some more probable.
Which one?
Argon. I mean, having a UJ from argon directly by knocking out the argon components.
Oh yeah, because energetically it is higher, lower potential.
Within the same atom, I mean, the transition probabilities are much.
So what
Probably I didn't get your comment properly. Sorry.
So you can knock out the argon core level and then create two holes in the 3p level. That's the thing. The OJ process.
Just the regular inertial OJ process. In the
Okay.
argon can also be done.
Okay. Yeah, it can also be done. But that will be more. But if you have a hole in 2s, this is the only way it can. There are many ways to go. One of the ways you can see that this level is above many of them. So you can also. What I wanted to show this is to show the electron transfer mediated decay process as an example.
energy has to be different
Which one?
Direct OJ
on argon?
in argon.
Yeah, it will be different.
So that's what.
Yeah, it will be different. Yes, you can do that. Yes. So all these experiments are coincidence experiments where you can actually measure the electron energy and stuff. Yeah.
The OJ energy would be
Different. So this is when both ICD and this ET, electron transfer mediated decay, are possible. It is found that ICD is dominating. And if you have many ICD pathways, that is, an atom is there and the de-excitation could release an electron from neighbor. But if you have several such possibilities channel, then the ICD rates rise up. So, for example, this is the best candidate to look at it is an endohedral system. So, where you have several surroundings. So, in this system, an inner inner vacancy in the neon atom could get filled by the outer shell electron, and the energy could kick an electron from the cage. Okay, so there are several channel possible. So the ICD rates are exceedingly high for this system. Now let us see something very interesting here. If you consider neon within carbon, C60, the 2s hole neon with C60 is energetically above 2p hole neon plus C60 plus, which means that this state could decay to this via ICD. What I mean is this 2s hole will decay to 2p hole and the excess energy will kick an electron from C60. So I'll end up getting via ICD, I can get these states. But it is also interesting to note that some of these levels of neon plus C60 plus is above neon C60 triply ionized state, which means I can, from this state, there could be an electron transfer from C60 plus to neon and neutralize it, and then excess energy kicks an electron out from C60. So you get a electron transfer mediated decay to this state.
Aravind, can I have another quick question? Yeah. What is the quantum yield of such a double ionization, in the sense this neon plus C60 plus? Now you are looking at completely different atoms, set of atoms, right? So per photon of the X-ray,
yeah,
how many such states can be created? Yield of that?
Oh,
is it small? Is it large? Is it 100%?
Oh, it depends on the transition amplitudes between these, right? So when you evaluate the ICD rates,
that's right.
So you have a cascade of transition with differing probabilities. So all are possible with differing probabilities. So
the single photon,
yeah,
generally
single
ionization, not double ionization.
Exactly. Exactly.
Unless there is electron correlation.
Correct.
So that makes the probability much less double ionization.
Right. Much less, right?
Much less, but I thought his question was like, how many possibilities of all the, or you're talking about from single ionization.
Suppose
Single ionization anyway will be dominant.
that's right.
But among these, it will depend on the ICD rates for individual transition.
Correct. So for example, in molecules, for example, we calculate the non-radiative processes, what the rates of the non-radiative processes are versus the radiative process.
Right.
And we calculate how much yield you can get of a non-radiative state. Right?
Yeah.
This is a non-radiative process, does not involve photons. So my question was, can I get 100% extraction?
Yeah,
That every time I can generate that?
Yeah, so what happens is whenever ICD and radiative process are both possible, ICD being faster, it is more faster decay. Now, you have this possibility. The other possibility, simple possibility, is that I can also have an ETMD from this state to this. And there is another interesting possibility from when you compare these two states where two electrons could get transferred. This is double. One electron from C60 gets transferred to neon cation, neutralizing it, and two flies off from this. This is called double ETMD. They are not verified yet. They experimentally verified yet. Now, is there experimental evidence for this ICD? We are talking about too many exotic possibilities. So, this was predicted in 1997, and the first evidence for that came 3 or 4 years later in neon droplets. However, a very unequivocal evidence came from neon dimer case. Okay, it's a very interesting, simple experiment. So what you do is, in this process of neon dimer, you create two holes, one in each monomer unit. So they have to fly off. Now, when you have a neon gas, you will have clusters. You have neon atom, and you have neon dimer, and so on, monomer dimer, and so on. And when you ionize neon atom, you get neon cation, which is going to have a much lower energy velocity. On the other hand, when you have a neon dimer, and if it is going to undergo this ICT, the unequivocal signature of the ICD is that I have two neon cations flying apart with equal and opposite velocity momentum. Okay, so there's a very clear sign of the thing. This is what was used in this experiment to measure the two neon cations they are flying apart in coincidence. So this was done using cold trims and synchrotron radiation. I'll just briefly tell you what it is. So you have photon beam intersecting the gas jet where you have neon clusters, and the ions that are formed, they fly apart with equal. The ICD ions, they fly apart with equal and opposite momentum. With an electric field, you kick them towards the detector, and if you know the kinetic energy that is released in this process, then for the electric field and the geometry of your system, you could always simulate the time of flights of the two ions, okay, that come from a single event. Every two ions that come from a single event, that is possible. Now, you see that the simulated times of flights of the two neon with both neon 20 is exactly measured, okay, and for the isotopes also it's exactly measured as per the simulation. It is a simple experiment. It's very clean sign of ICD. Okay, and so this is what, although there's an experiment before this, this is what we people discuss as an unequivocal signature of ICD. Now let us go in some detail here. Now, what about I told you that if you know the energy of this release, then you can compute the times of flight. So what is the kinetic energy released during this ejection? So that is nothing but the energy difference between the 2s hole, because you're creating the 2s hole to begin with. Energy difference between 2s hole and two neon atom with 2p holes in it, but they are asymptotically separated. So if you know this difference, then you know this energy. So 48.48 is the energy of this 2s hole, which decays into two 2p holes, and this is the excess energy that is released. Now, this excess energy needs to be shared by the ICD electron and the kinetic energy of the two ions that are flying apart. So you can see a very nice experiment that the result for this So this is the total energy, 5.16 eV. Now, the photon energy that they used is 58.8 eV, okay, which is below the one-side double ionization. However, it could create the 2s hole, and hence this 2s hole could decay into an undergo ICD and create the NE. So you don't have a doubly ionized system from one single. Even in the dimer, you cannot have it from one single unit. So then this was used. So if you use 58.8 eV and create a 2s hole, the 2s hole is at 48.8 eV. So the 10 eV is the photon energy that you get as per this calculation. And you see that that is what is measured. What this plot shows, the kinetic energy released versus the electron energy. And you see the photoelectrons lumping here, energy. And very interestingly, you see the straight line. It has to be a straight line because the energy is shared between the two nuclei and the electron. The electron takes the most of the energy, then this guy gets the minimum energy. Okay, the share depends on at what point it exploded. K is the kinetic energy release when they fly apart. And you see that exactly when you have the maximum electron kinetic energy and you add this, it is close to what you expect, 5.16. So it's a very clear signature of ICD in this system. Now let us go to some different kind of ICD. I have
electron energy measured separately or the same code?
It's same code in coincidence with this. So you have collective ICD. There is yeah.
The accuracy. When you really need to.
Sorry.
Because coincidence means that both are detecting at the same time.
Not same time. It is about you correlate the events, every events that they collectively form one event. Every hit, there are electron hit, ion hit. They have to correlate to combine together to form one single event, correct event.
So is there
That's what
involved in terms of time when you're correlating that?
Yeah, it depends on the electron energy and the electron energy and your time. The electron time of flight is different from the ion time of flight. So it's typically done very simply.
I was just wondering that you are having two events where two ions you have got
flying apart.
You put an electric field and they
Correct.
hit the detector.
Correct.
So you need to know that they are hitting at the same time.
No, they won't hit at the same time. That's the point. They don't hit at the same time. See, I showed you the previous one. This is sorry. I just show you that. This is the time of flight of first ion, second ion. They have to form that. Yeah.
So what is important?
Yes.
Also, what is the potential background? Like this kind of whatever you said that coincidence going in the two side. I mean,
Not two side. Both the ions are going to.
That the
electron is going to another opposite side. Yeah, correct.
This kind of signature from something which is not the real signal.
Yeah, you can get it. You can get it. You need to. Yeah, you see, for example, one of the most important thing is an electron from neon monomer singly ionized. Fortunately, the corresponding neon cation will have a momentum, almost zero momentum, because zero momentum in the sense in the center of mass frame, what you created. So you can get rid of them. Yeah.
Also, they will not contribute to you. They will contribute in the random.
Yeah, they will not be. Yeah, exactly. Now, so this is a very interesting. Now we'll turn our attention to a different kind of ICD, where I have helium dimer. Okay.
Can I just ask a question?
Yes.
I'm just thinking about this data, the two-site ionization, which was around 45.
Correct.
And the single site for one electron ionization for the 2s or 2p, sorry, 2s. 2s is 48.
Yeah.
The 3V difference.
Correct.
That isn't it like some sort of a binding of the cation, the dication with respect to the cation, some sort of a stabilization of the dication, the 3V difference.
Yeah, there's a 3V difference, which means that the 2s could decay to the 2p holes for sure. Then So what happens?
Right. No, I was
3eV is pretty large for making it this transition also more plausible.
Right, but okay, we'll talk about this later. You go ahead. Yeah.
Okay. So if you have a helium droplet, okay, and if I do bound, what I do is I shine light to this helium droplet, and I do bound transition in I'm not creating any hole, but I'm creating bound transition in two neighboring helium atom, and they can be part of a helium droplet. And when one of them de-excites, the energy could be transferred to the second one, and the electron could be ejected out. Okay, there's no hole that is created, but this is called collective ICD because the energy is not initially dumped in one site of the dimer. Both the units of the dimer are actually picking the energy. One de-excites, transfers the energy to the other, and that is an electron flies out. Now, this was also experimentally verified, but then we need to note one important point here. The photon absorption, the order of photon absorption is a single photon process, because each of these guys are undergoing single photon absorption. The next step is about transfer of energy, which is taken care of by the electron-electron correlation. It has nothing to do with the photon. Although two photons are involved, it is a not multi-photon process. Okay, this needs to be so this was proposed, and it was also verified. What they did was they took helium droplet. The ionization potential of the helium droplet is 24.6 eV. Okay, of course, these things slightly could differ with the droplet. And there is a transition from 1s2 to the excited level, 1s2p. So you take one electron from the 1s level and take it up to the excited state in both the adjacent helium. One of them drops and the energy is IC transferred and the 2p electrons fly off. Now, when this happens through many of these helium, you form helium cations, they undergo Coulomb explosion and they just go away, they get repelled away and they fly off. Now, the most important point that we need to recognize is, if you look at the yield of this helium cation, the ln of the yield of this helium cation versus the laser intensity, ln of the laser intensity, for this process, the plot will be having a slope which is equal to 1, should be 1. Now, what they did was, I don't know why this is. So what they did was here, you look at the red color one, it's 42.8 eV, which is much above the ionization potential. The slope is naturally 1 because it is a single photon ionization. On the other hand, if you take blue color points, they are 20 eV. It is not resonant with any bound transition in helium. So if you get a helium cation signal from this, it has to be a 2 photon process, okay, at this intensity. So they got a slope of 2 for this. Okay. On the other hand, for 21.4 EV, which is resonant with this transition, okay, they get slope of 0.63. It is 0.63 because the bound transition is actually saturated. So it is not more than 1. It is less than 1. Okay. So this is a clear indication that you have a collective ICD that is happening. You cannot have the slope otherwise less than 1. Now, so what we have done so far is to see, we have the ICD has also very recently this year has been measured in liquid water as well. There are 2 classes of ICD that we just saw. One is the initial in one case, initial excitation de-excites and kicks an electron from the neighbor. For this, you need extreme ultraviolet photons. In the other case, you have collective ICD, where you just need to excite a bound transition, okay, and then then ICD happens. This is called collective ICD. All the ICD that we know so far can be classified into these 2 divisions, classes. In this case, you need high intense photons. In this case, you need high intense photons because you are creating a bound transition in a dimer. Both of them have to absorb photon, they are close by, which means that they both have to have photon in that very small spacing. Intense photon density should be available for this to happen. Otherwise, one will absorb and radiate till decay and it will not happen. So The issue is that the bottleneck is that you need high intense laser photons. On the other hand, for this, you don't need that. You just need EUV photon. And the advantage is if your transition is in lower, longer wavelength, you can always use.
Can I ask, is there any wavelength dependence to this, or you can use anything that shows a resonant by bound transition?
Yeah,
any lower energy than any of the core or the
yeah. So you in ICT is essentially between the inner shell, inner valence and outer valence mostly. Unlike OJ where you have core electrons, right? And yeah, if you're resonant with any transition, you should do it. Of course, you should also have the energy should be sufficient to kick the electron off. Of course, not that much. Yeah, right. Yeah. Okay. So the commonality between these two classes is that both work only in clusters. Okay. So the question that we ask now is it possible to observe ICD in unbound systems? Okay, to begin with. And we need the molecules to be very close by. They have to be interacting so that I have ICD rates reasonably high. But if you have unbound molecules, this is not possible. So what we do is we take unbound molecules which have good interaction, okay, but they are not bound together. And if you have such molecules in their excited state, such interactions could be amplified. One such nice example is pi electron molecules, where they, pi stacking, they interact, they form, for example, pyridine forms 3 stacked together. And if you excite pyridine, then there is a scope for these interactions to be amplified, and maybe they interact more, and then ICD could happen. So this is what we wanted to check. What we did was we took pyridine monomers and excited it with 266 nanometer photons, very low intensity. It's very important to note that it's very low intensity photons, and we observed the formation of cations. Now this is intriguing because how do we form cations to begin with? The one photon energy, single photon energy is way below the ionization threshold. Okay, so you cannot ionize this by a single photon. You cannot create a pyridine cation with just one single photon of 266 nanometer. So the question is whether it is a multi-photon ionization, or are we having a 2-photon ionization process here? 2-photon process. The pyridine is absorbing 2 photons together. The problem is that we are working at very low intensities and we are observing this. Okay, typically you need high intensity. This is an unfocused laser. Okay, we are not focusing. We have to create any high intense MPI, multi-photon ionization. It's unfocused laser at such low intensities, but still we wanted to look at whether it is a 2-photon ionization. If it is a 2-photon ionization, then the maximum kinetic energy of the photoelectrons will be 2 times the photon energy minus the ionization potential, which is 80 millielectron volt. But our measurements show electrons with energy more than even 500 millielectron volt. Okay, it's much higher. So clearly it is not a 2-photon process. It's 3-photon process. Well, when a 2-photon process is possible, that is more probable than 3-photon process. Most importantly, the electrons from these process was also ejected isotropically. This is not possible for a multi-photon ionization, because if you do a multi-photon ionization, the electron that comes out will have an angular distribution with respect to the laser polarization, which will reflect the type of orbital from which you ejected the electron. So you typically expect an angular distribution about you don't expect an isotropic emission. So the isotropic emission of slow electrons here rules out MPI.
What about the intense fluence dependence that you did? For example, how much cations you get depending on the intensity of the light? Does that have a slope that is more than 1?
This is a very important part.
Okay.
This is a very important part. I'm going to do that. So isotropic emission of electrons rules out MPI, multi-photon ionization. Now, the second question that we need to ask is that, in fact, the first question that we should ask, how do you form ions which are larger than the parent? You have heavier than parent cations. Oh God. So you have, why this is happening, I don't understand. Okay. You have heavier than parent cations. Note that I have a mass at 106 which is greater than 79 AMU. We have reduced the yield. When we have for plotting, we have just for presentation, the yield is factored by 10. So you have ions that are heavier than monomer, yield is higher than the monomer. Okay. You also see ions that are greater than dimer, right up to dehydrogenated trimer. So we need to answer how we get the heavy ions as well in this process. Interestingly, under the same experimental conditions, when we do electron impact ionization, we do not see any of these heavier than parent cations. This is a very important point. We see only the parent and parent minus with a HCN loss. Okay, so there is something that is peculiar about this the transition that happens with 266 nanometers. And the other important question is that how do you form ions? Some of these ions have appearance energy as 20 eV from pyridine. Okay, that is a minimum energy that you require to create that particular cation. So some of them are 20 eV. So where do you get 20 eV? We are talking about 2-photon process that is much lower. So these are the questions that we need to answer. So what happens in this excitation is that when you have a 266 nanometer, there is a resonant pi star transition in pyridine that is happening. So there are all the pyridine monomers, they undergo this transition. When excited monomers undergo this transition, and if they are interacting, okay, we do not know yet, if they are interacting, then energy transfer, like in the case of collective ICD, could happen. Energy transfer from one of them could get into the other and ionize it. This is possible. However, so what we did was sorry, sir, 1 second. No, we didn't see. No.
Even in electron impact?
No, electron impact also we didn't see. We had where is that? This is I'm not doing very bad here on this. We don't see, sir. We see only the parent and the HCN loss.
Can I ask a question? Yes. Can you view this process as an excited state electron transfer rather than an ionization? Say suppose I dope in a quinone along with the pyridine.
Okay.
Would I see a cation formed and the quinone anion radical, for example?
I dope pyridine with another species.
Quinone as an acceptor, electron acceptor.
Okay.
And do the same pi to pi star. And it's just an electron transfer between donor and acceptor.
Yeah.
The donor is pyridine and the acceptor is.
Yeah.
Can that be also?
Can happen.
Okay.
Can happen. Yeah. So what we did was Sajeev from Sajeev is he's here, right here. So he calculated the interaction between the two excited monomers, and in the ground state there is not much association that is happening, but in the excited state, interestingly, at even a 10 Armstrong distance, there is a associative covalent interaction between the two excited monomers. Okay, so they form it's a bond forming association. So you can form a dimer. It's a bond forming association. So the pi star excited molecules undergo a bond forming association. This is what the calculations show, and you can also see that if you consider the trimer, the wave function overlap is extraordinary. So it shows that excited monomers, they can actually associate. There is an extraordinary association of excited monomers up to even this trimer could be formed. Now, if you have a dimer to begin with, that is, two excited monomers are there and they are associating to form a doubly excited dimer, then the total energy in this dimer is just 80 millielectron volt above the ionization potential, which is too small, and IVR could actually set it off resonant for ionization. You have two molecules, okay, 40 millielectron volt in each. So IVR could easily set it off resonant. So the dimer could be pretty stable. I mean, it could be a source of 2-photon energy. And when there is another excited monomer, there is an association between the three excited species. And when there is an association, en route to association, ICD occurs. There is these two electrons de-excite, Okay, pi star de-excitation, and the energy is transferred to kick the ICD electron from the excited monomer unit. So this is a three-center mechanism. Now, what's an important point here? I'm trying to answer your question. If you consider the collective ICD, I had a bound transition, same as this, and it is a single photon process. But there, it's a helium droplet, and you had everything nearby. The neighbor is there already. But on the other hand, here, although it is a single photon process, three guys have to associate essentially. Okay, so you expect the slope to be 3, and that is what we get. Okay, so the rate determining step is essentially that three guys have to associate. Even for forming pyridine, this is the slope that we get for pyridine, and it is 3, which means that this is the three have to collectively associate and create this three-center mechanism. So this is what we observed it, and we observed this not only in this pi molecule. We have few other pi molecules that we did. We also observed this. One interesting thing is in pyridine there is a n pi star transition also, and it falls at 355 nanometers, which is 3.5 eV. 3.5 EV, 3.4 EV. Two guys can't ionize it. You need 3 photons for that, and we see these heavier than parent with the 355 nanometer as well. Yeah.
I did not understand why this slope should be 3. I did not understand why the slope should be 3.
Okay. Now you expect it's a collective ICD, correct? But then you don't have, for this ICD to occur, you need to have them at a distance where they can interact. The excited monomers could interact. Okay. But unlike the helium droplet where you have it's a van der Waals cluster, everything is nearby. There is just one process that happens. This first process is excitation, and then there's electron-electron correlation that creates the ICD. On the other hand, here I create 3 excited monomers, but the rate determining step is that they have to associate. Unless they associate, ICD is not going to happen because it's not a cluster to begin with. So it's a very clear indication that it is an association that is happening. Otherwise,
I think that in the density of thing and so that check that your molecularity comes out to be 3 or the order comes out to be 3, changing the concentration. So I would think that typically if you want to have an association and determine what is if it is a 3 species reaction, you change the concentration or the density and plot it, and that slope should be 3, and then you get a
density versus the yield of cation.
Yeah. Right. I mean, see.
Number density.
Density of
correct. Correct. But here I think it is much more. This is much more relevant. This is much more relevant, I think, because what you have is you have the point is in the collective ICD. This distinguishes the collective the difference between the collective ICD and collective ICD with association. So that is why I think this is more important than that. Of course, you have when you change the density there also you should get the slope 3.
Yeah, no, along the same lines. I mean, like, if you change the concentration, because essentially your radiative process, right, that is less competitive as compared to this ICD because the ICD is happening very fast. But here, the rate limiting step
is which is radiative process here.
Right, the 2 pi for the dimer. Right, the 2 pi stars actually relaxing back.
It is not a radiative process. What you this sign is not a radiative process. This is a ICD.
No, that's right. But what I'm saying is, if the trimer is not present, if the third is not present,
correct,
then you would have a probability of just radiatively, recombining. Right, that's a slow process. But now with concentration, if you change the concentration, you may actually make it competitive.
Okay, correct.
Right. So I
agree. Yeah.
So would that actually show up if you did a concentration dependence?
Yes.
Right. So the slope should go down from 3 to 2, I guess.
Correct.
If you're actually doing concentration dependence.
If you go for a higher concentration,
lower concentration. Concentration. So less probability for the third trimer to come in.
Yeah. I think we are seeing this. We have this data. Yeah, we are having For other, we have something around 2.3 or something like that. Yeah, we have measured this. What we did was the line, the line we have pyridine at vapor pressure, we pumped it to lower pressure. Otherwise, it's essentially vapor pressure in the line. So we did this experiment. Yeah, at lower pressures, we get a lower slope. That's it. Yeah.
Oh, sorry. Yeah.
So what is the time scale of this ICD electron ejection over here?
It's in femtoseconds.
And then, but then the cluster is being formed after the excitation, right?
Yeah.
And the cluster formation is the rate determining step?
No. What you have is excited states, okay? And en route to the cluster formation, ICD occurs. So before even the full association occurs.
Yes, but then how fast are these cluster formations? These should be diffusion of the atoms, right? Molecules here. Yeah, sorry.
So why should you? It's about. Okay. See, when I say ICD is fast, when you have the neighbor and you have two processes that are competing, I say ICD is fast with the femtosecond time scale. When they are far apart, there is no possibility ICD channel is not active. When they come close by, what time they take, they come close by, they are excited, and ICD occurs at a very fast time scale.
Okay. Then my question.
Actual association could be later. I mean, it will be slower than this.
Okay, then my question is, by the time they come together, does it not de-excite?
Without even doing ICD.
Yes.
Yeah, it could happen. It could happen. Actually, what we have here is we create something like 10 power 15 excited. I mean, we calculate the density and the photo absorption cross section of pyridine. We create about 10 power 15 photo excited monomers. Okay, and we see per shot 20 or so. And another important, this is because they will also get de-excited. Another important point is in pyridine excited state, it goes from S0 to S1, and from S1 it goes back and forth between the higher vibrational levels of S0 and higher vibration. When you have vibrational excited state, they decay slowly. So when you go back and forth, the lifetime, there is a component of lifetime which is longer as well. So these are mostly from those species.
Okay, so
the quantum yield is far low. The quantum yield is far low. Yeah.
So what are the typical lifetimes of this excited pyridines?
Yeah. So if you consider excited pyridine, you have the fastest one is in picoseconds.
Okay.
But you also, when the one that it talks about, the transition between S1 and S2 vibrationals are in microsecond.
Okay. And one more question. So you need two de-excitations for one ICD electron ejection?
Correct. Okay, you have a point there. It's not required. I mean, you can also have one de-exciting, okay, and ejecting this electron. The third one could be of some use. I'm going to do that. I mean, it will require some extra energy for fragmentation also. So that comes from the third photon. There are two mechanisms that we propose. One is this, where we have 3-center ICD. The other one is you have 3 guys, but 2 of them share the electron. The other one is responsible for the fragmentation. Yeah. Otherwise, it's important to take out the loss through IVR. Yeah.
What is the typical energy for this de-excitation from pi star to pi when it comes?
4.6 eV.
And that is enough for the ICD electron ejection? Right?
Yes.
Okay.
Because 2 of them add up to get, it's more than the ionization potential.
So just to clarify, the entire thing is happening for only pre-organized clusters. If you think about it,
no. You mean the ones that are the
accidentally close by.
Yeah.
Those are going to have the 3 excited states come together. Like, we don't have the time for these things coming together after excitation.
Yeah.
It's so fast that you need to have pre-organized clusters.
Correct. Okay. That's true.
Okay.
But there is something very interesting also, but in a different situation. People have found that it's not related to what we are doing it in gas phase, but there are also in the liquid phase, people have found attractive dipole interaction, interaction of molecules, pi-excited molecules that are separated by 100 nanometers. So this year, this paper has come in. But the situation is entirely different. Yeah.
So you don't have any excimer kind of formations in the systems? One is in the excited state, other in the ground state. And also the energy level will go down.
But it can happen, but you don't ionize the system, right? You were saying one is A star B.
Yes.
Yeah. But it can be there, but you cannot. So there is something people talk about cycloaddition where you have one of them excited and the other one is not excited. You can have them forming a dimer, but they won't undergo ICD.
But no, this is not actually, there is no cyclization kind of thing, just a weak bound system.
Okay.
Weakly bound system. So there also the
dimer is a dimer system.
You can say dimer, yes, excited state dimer.
Yeah.
So in those system also, when the third molecule comes in.
Okay.
So I'm asking how this is when you say three-centered system.
Oh, okay. So what you're saying is up there a dimer which is
yes,
singly excited.
Yes.
And I have another one coming.
Yes.
The association.
Yeah.
They have two excited ones. And again, the same story, right? I mean, I am 80 millielectron only above the ionization potential. So again, IVR could be making it too worse now because I have another guy in.
Yeah, one more. In case of pyridine, the association will happen sideways because it's a pi molecule.
Yes.
So how the three-centered system forms?
You have a pi-stacked system with three phases together, right?
Okay.
It can form.
But in the last slide where you showed the hybridization, can you just
it was co-facial only, right?
Yes, here.
So
when you say here how this happens, because pi molecules used to come in the sideways. So here it's sideways?
It is sideways only.
It's sideways.
Yeah, sideways.
Okay, but it looks like no. Okay, thank you.
Now, so God.
There's one more question from a student.
Just 1 second, let me just, you can ask the question. I want to go back to what I was. Yeah, so can I just finish one point? Yeah. So what I have here is finally this trimer cation that I form is energetically, I have association energy that is released. And so the trimer cation will fragment to dehydrogenated trimer cation to all these different molecules, fragment cations. And the association energy that you get, we see about 7.5 eV as per the calculation, accounts for the appearance energy. In fact, the number is just above the appearance potential. So all that we observe in experimentally is explicable with this three-center mechanism. So yeah, this we recently got published, and the implication is that pi molecules are our entire biochemical environment is essentially made of pi molecules, and we are talking about radiant. Now if you have bound transition, and if there is an interaction, then you can have this ICD happening. So we have radiation damage at even ambient light, and ICD generally and as we just saw, they are forming heavier than parent cations, which means that this mechanism could lead to growth of molecules in the interstellar medium, because you excite them, they are associating. Light itself can enable this association. And ICD efficiently produces slow electrons. In water, liquid water, ICD produces surplus slow electrons, and we know that it is very dangerous for the single strand damage. So it was exciting to join Saroj and Sajeev in conceiving this three-center ICD. It was very exciting to discuss ICD with Rajesh, and Saurav and Saroj did all the experiments, and Saurav and Nihar also actively supported Saroj. Yeah. So I'll stop here. Thank you.
The talk is again open for more questions, but I'll start with.
Yeah. So you have some association energy release. So why you ignored that association energy in electron spectrum? Because you have 80 MeV threshold, and rest of the energy can come from association energy.
Rest of the energy can come from
association energy, because you have some energy release due to that association.
No, but okay. So there is what you find is you were saying the association energy can go out as an electron kinetic energy. But the ICD happens prior to association. En route to association, ICD happens. ICD just needs them to be close by. So what we have we are seeing is that there is 3 excited monomers and they are associating en route association. Before the association, there is ICD that is happening.
When they are getting closer, electron coalition will enhance because ICD depends on electron coalition.
Exactly.
So there is more chance of
ICD being faster when they are at the critical distance. ICD happens when the rates are there. ICD immediately happens. I mean, it occurs at a faster rate. So ICD happens before the association, and the association energy that you get is available for fragmentation. Otherwise, you cannot account for the available observed fragments.
Okay. Another thing I want to ask that only thing you need is 5-star excitation. So why don't this thing not happen for electron excitation? Electron impact excitation.
Okay. Yeah. So we have seen electron impact ionization also in some other molecule. So we have yet to confirm it. We have an electron impact ionization. Sorry, electron impact excitation. That's what you're saying, right?
Yeah.
Ionization or excitation?
Excitation.
Yeah, excitation. We have seen signs of forming larger molecules in some other system. But we are just working on that. But in pyridine, we are not seeing it. We are seeing only parent and lower than parent.
There's a question here.
Yeah. So I'm slightly confused. Maybe I missed a link somewhere where you call your bound versus unbound systems. So, like for example, you talk about helium dimer and neon dimer, and you call them bound.
We're bound in the sense that they are van der Waals clusters. Yeah.
Yeah.
Weakly bound. Yeah.
So even in your case, like pyridine dimers or trimers,
yeah,
even they are bound by some pi stacking interactions. Like
correct, exactly.
So like, what is the difference between this bound and unbound? And I don't understand.
Yeah, you have a point. It's about to begin with. Prior to excitation, they're unborn. What is interesting in this system is that you don't have apparently you don't need a bound system. You start with the unbound system. You excite them and you have interaction. Okay, then they become bound. You need to be having interactions for ICD to happen. So we say that it is an unbound molecule because it is happening prior to excitation.
I'm confused because you said that this ICDs occur only if you already have these trimers existing, or like if you already have these 3 molecules of pyridine closer physically.
Yes.
Only then this
correct.
This process will occur.
Correct.
So
no, that 3 molecules are closer, they associate and they come closer, the ICD occurs. Prior to photo excitation, they are unbound.
Ground state is unbound.
Ground state is unbound. Excited state is associating.
Okay. Yeah. Thank you.
Confusion on that, but we will. Yeah.
Yeah. I mean, actually, I have a question regarding the neon dimer, right?
Yeah.
So you no longer have a spherical symmetry. So
correct.
Can you distinguish the 2p Z channel versus X and Y channels when you get the ICD?
You are talking about there is no Runge lens vector that is conserved in neon. The spherical symmetry, it's not 1/r potential. Is that what you're talking about?
No, I meant like the 2p X and Y. They won't be of same energy versus 2p Z. So do you distinguish these 2 channels on your ICD?
Well, they are very close by, right? They are almost degenerate.
Even in the cation, like when you have any 2+.
Okay. That I am not sure. Yeah.
Okay. Yeah.
But then if you have sufficient energy, any of them will have. So when you calculate the ICD range, you need to average it over all these channels.
Okay. Yeah. Thank you.
Yeah.
When you did electron impact ionization, you had single collision condition or multi collision?
Single collision.
Single collision condition. Then in that case, you cannot see ICD.
Why? Single collision condition means why do you say the single collision condition?
Simultaneously, electron not exciting many pyridine atoms.
No, that is not single collision condition, right? We don't call that a single collision condition. That is, even you can have several electrons here colliding with several molecules. Still, it is single collision condition. That is not that we mean something else by single collision.
Yeah, mean at one time multi pyridine excitation by electron impact.
It's different. Single collision condition has a different meaning.
Okay.
What you are saying is, I have several pyridines. Each of the electrons, there are many electrons exciting them, each of them, and it's not single collision condition. You are saying. Is that what you are saying?
I mean, I may be wrong in term, but I am saying like photon case, why you don't have multi pi star excitation due to electron impact?
Okay, that see, it depends on the excitation cross section, right? For the energies that we used, it depends on the excitation cross sections. You know, we have not observed in a couple of molecules. We have studied this in 3 different molecules. This for the entire system. Okay, out of which 2 of them do not show this with electron impact. Only the other one we are observing this kind of ICD with electron excitation. So, but we are not sure. We wanted to really study this more in detail. We want to perform this experiment again. Yeah.
You might have checked, but related to his question, what I am suggesting that did you check this as you're saying also the concentration dependence or the as a function of pressure? Then that will clarify your single collision condition. That is the way to check, right? As a function of pressure, yield as a function of pressure.
True.
If you see, I mean, if it's a linear behavior or not.
Yes.
If you have to,
yeah, it will show.
That is a single collision condition.
Exactly.
That's what I'm trying to say.
Yeah. But single collision condition, I thought what he is talking about is different. He is talking about a different single collision condition. I think so. Yeah.
Yeah. So I had a slightly different. So I didn't quite follow the mechanism of association. And how general is this mechanism that you're able to extrapolate that to interstellar, formation of molecules?
Yeah. So you see, if you have this pi star interaction, so what is the problem? Why is it an issue with the interstellar mechanism? In the interstellar mechanism, when you medium, if you have sufficient density wherever, I mean, it's not in the interstellar mechanism. Interstellar medium is rarer. But at least the point where from the circumstellar envelope where the ions or molecules are ejected. So there if you have this kind of interaction, you can form larger molecules.
You can, but in terms of a dimer becoming a trimer versus higher mers, right? There is a rate limiting step in terms of their collisions, for example.
Correct.
So and in between your ICDs can happen between dimers, it can happen between primers.
True.
So once you have that, then
you don't form the larger ones. Correct. True. Yeah.
It needs to be limiting.
Yeah.
The limiting process.
Yeah, I agree.
Last question, and then we'll go for tea.
Okay, so actually I could not follow the energy criteria for this pyridine ICD. So when you have a monomer pyridine, what is the energy required for the electron removal? 1 electron to the dissociation level.
Monomer PDD. I didn't hear you properly. What is it?
Monomer pyridine.
For a monomer
pyridine.
Yes.
Okay.
What
the energy required is around 9.24 EV.
And when you have this cluster, how much is the energy required?
Slightly reduced.
Slightly reduced. Okay. Now when you so now you're giving a light.
Yeah, but then we don't consider that because when you have molecule, when you have dimer is fine, but otherwise when they are associating, the ICD happens before the dimer is formed.
Okay. Now you are putting a light of 266 nanometer, right? That is around 4 point some EV. So that is so that excites from pi to pi star.
Correct.
And then you have a de-excitation from pi star back to pi. That will again give you around 4 point some energy.
Yeah, or lower than that. Yeah.
Lower than that. So how does that enable for the electron removal in this cluster? I still don't get it.
There is an de-excitation.
Right.
And then
But he has excited 3. He has excited 3 simultaneously.
Oh, so it's a 3.
All 3 are excited.
3 photon.
Yeah.
Okay.
All 3 are excited.
Oh.
2 are de-excited.
And 2 are de-excited.
2 are de-excited. After only one is de-exciting and sending the energy to, transferring the energy to the other already excited one.
Okay. The other is also excited already.
Yeah.
Okay.
All 3 are excited.
Okay. Thank you.
So let's get bound.
Thank you. Yeah.
Thank you. That was wonderful talk, Aravind.
Thank you.
Also.